Hello everyone, welcome to the chemistry channel. So today we're going to be discussing effective nuclear charge, and the first thing that I want you to imagine is a one electron atom. So in this first scenario, in scenario 1 we have two different conditions, condition A and condition B. In condition A we have a +1 charged nucleus, a -1 charged electron, and a distance separating the two species equal to r. In condition B, we have a nucleus with a +2 charge, a electron with a -1 charge, and a distance between the two equal to r. So which condition, condition A or condition B, do you think will produce a greater force of attraction between the nucleus and the electron? So hopefully you said condition B. And the reason why is because the nucleus has a greater charge than condition A. And you can predict this behavior through Coulomb's law. Coulomb's law is used to describe the force exerted between two charged species. So Coulomb's law can describe forces of attraction and forces of repulsion. So Coulomb's law is equal to a constant times the charge of both species over the distance between the two species squared. So from this relationship, you can predict the force of attraction or repulsion between two charged bodies. So if the magnitude of your charge increases, the force between the two species increases, and if the magnitude of the distance increases, the force between the two species decreases. So let's look at scenario 2. Scenario 2, we have condition A and condition B. Now in condition A, we have a +1 charged nucleus, a -1 charged electron, and a distance between the two species equal to r. And then here we have, in condition B, we have a +1 charged nucleus, a -1 charged electron, and a distance between the two species equal to 2r. So it's twice the distance as that of condition A. So which condition do you think will produce the greater force of attraction? So hopefully you said condition A. And once again, this is because Coulomb's law states that as the distance between two charged species increases, the force between them decreases. So now I want you to imagine a multi-electron atom. So in a multi-electron atom, things are a little different because now we have to account for other electrons. So let's look at this electron here. So this is our electron of interest. So this is our electron of interest. And let's map out the forces acting upon this electron of interest. So let's change my color here to pink. So the first force that we want to map out is our force of attraction. So the force of attraction occurs between the nucleus and the electron here. So let's draw the arrow. So we have an inwards pointing arrow. So this inwards pointing arrow is basically telling us that the nucleus is attracting the electron towards it. So this is our force of attraction. So let's just symbolize it as that. This is our force of attraction. However, we also have this electron here. This electron is going to repel our electron of interest because like charges repel each other. So therefore, we're going to put a little arrow pointing this way, indicating that it is repelling our electron away from the nucleus. So this is our force of repulsion. So the net force acting upon our electron of interest would be equal to our force of attraction minus our force of repulsion. Now, we're not in a physics class, so I'm not going to go into the equations. I just want you to grasp the concept here. Because let's compare this to a single electron species. So let's just draw the forces acting upon the electron of interest, in this case this electron because it's the only one, and for this condition. So the only force that's acting upon this electron is an attractive force. So let's just say force of attraction. So we can clearly see here that the force of attraction acting upon this electron is less in the multi-electron scenario than in the single electron scenario. And that's because the single electron scenario doesn't have repulsive forces pushing this outer electron away from the nucleus. However, in our multi-electron atom, the electron is pushing our electron of interest away from the nucleus. Therefore, our overall force of attraction is decreased on our electron of interest. So therefore, when you incorporate more inner electrons, so if you have more inner electrons, our force of attraction will decrease. So let's put that in words. This means that the force of attraction on an electron in a multi-electron atom is less than the force of attraction on an electron from the nucleus in a single electron species. So note that the more core electrons you add, so the key to know is core electrons. So the more core electrons you have between your outer electron and your nucleus, the less your force of attraction. And that's because you have these repulsive forces. So if you had even more negatively charged electrons in between our electron of interest and the positively charged nucleus, so say you had an electron here, these two would also repel the electron. So the more electrons you have in between your nucleus and your electron of interest, the less of a force of attraction you have. So we can extend this idea to charge. And we can sort of make sense of this because the force of attraction or the force of repulsion between two charged bodies is directly proportional to the charge of the nucleus, so the positive charge. So as the positive charge of our nucleus increases, the force of attraction towards an electron increases as well. So since we can sort of extend this idea to charge, we can say that the charge of the nucleus felt by an electron in a multi-electron atom is less than the charge of the nucleus felt by a single electron atom. So once again, the charge of the nucleus felt by an electron in a multi-electron atom is less than the charge of the nucleus felt by a single electron atom. And once again, this is because of our repulsive forces. And this modified charge is called effective nuclear charge, or Z effective. So Z effective is the effective nuclear charge. And it's basically the charge of the nucleus an electron feels. So it's basically the charge that an electron feels. And in order to find Z effective, all you have to do is use this simple equation. So Z effective is equal to Z minus S. So what do all these things mean? So Z effective is, of course, the effective nuclear charge. Z is the nuclear charge. So this is the actual nuclear charge. And note that Z is just equal to the atomic number. So the number of protons in your particular nucleus. And S is the screening constant. So S is the screening constant. So what is the screening constant? Well, the screening constant is what is the constant that takes into account the repulsive forces of electrons in between. So in between, that's important to know, the nucleus and the electron of interest. So the screening constant is the constant that takes into account the repulsive forces of the electrons in between the nucleus and the electron of interest. So basically, let's just say you had a positive charge here and you have your positive nucleus here and your electron here, and you have all these electrons in between. And you have this force of attraction acting upon this electron and all these repulsive forces that are pushing this electron away. And what your screening constant does is it takes all these repulsive forces into account and puts them into one number so that you can calculate your effective nuclear charge. So we can actually estimate the value of the screening constant by using Slater's rules. So Slater's rules are basically this list of rules that you have to memorize in order to be able to calculate the value of S. So I have typed out for you all of the Slater's rules, all of his rules. So the first thing that you have to do is organize the electronic structure of your atom in this particular way. So the first thing that I want you to notice is these parentheses. So the parentheses that surround the 1s subshell, the 2s and 2p subshell, the 3s and 3p, and so on. Each of these parentheses distinguishes a group. So the parentheses around the 1s state that this is group 1. And the parentheses around the 2s, 2p state that this is a group 2. So each of these parentheses are a particular group. And you have to organize the particular subshells in this particular order. So you organize them by increasing n and l value. So you go from 1s being the lowest, then 2s 2p, 3s 3p, 3d 4s 4p, 4d 4f, etc. So they have to be organized in this particular way. So now we can get into the actual rules. So the first rule is that each electron with a principal quantum number higher than the principal quantum number of the electron of interest contributes 0 to the value of S. So let's say that we have an electron in the 2p subshell. So we have an electron in the 2p subshell. When you're calculating the value of S, you would not consider any of the electrons past the 2p subshell. So if your particular atom had electrons within the 3s subshell, you would not consider those electrons in your calculation of S for the 2p electron, because any electron that has a principal quantum number higher than the principal quantum number of the electron of interest contributes 0 to the value of S. So the second rule is that each electron within the same group of the electron of interest contributes 0.35 to the value of S. However, there is an exception, and the exception is that the 1s electron contributes 0.30 to the value of S if the electron of interest is within the 1s subshell. So in order to understand this one, let's do the same thing. And the same thing, we're going to look at the 2p subshell again. So recall first that each electron within the same group, so the same group of the electron of interest contributes 0.35 to the value of S. So what do I mean by the same group? Recall that parentheses close off each group. So in this case, if we're looking at the electron within the 2p subshell, we're looking the whole group here. So this is the whole group. So you would count all the electrons within this group. So let's just say we have 2s2 and then 2p4, right? And our electron of interest is in the 2p subshell. So each electron within the same group of the electron of interest contributes 0.35 to the value of S. So, if we're looking at an electron within the 2p subshell, we would just count all the electrons within this group besides that electron of interest. So we would take 3, not 4, because we're not counting our own electron, plus 2. So that would equal 5. So then you would multiply 5. So remember that 2 comes from the 2s2 and the 3 come from the 2p subshell. And we will multiply that 5 times 0.35. And whatever that comes out to, we would add to our S value. So that is rule number 2. So rule number 3 is that each electron in groups with a principal quantum number of n-1 compared to that of the principal quantum number of the electron of interest contributes 0.85 to the value of S. So once again, let's look at our electron within the 2p subshell. So in our electron with the 2p subshell, so what you would do in order to find that S value is multiply 0.85 times 2 and then add that to your S value. So the fourth rule is that each electron in groups with a principal quantum number of n-2 or greater compared to that of the principal quantum number of the electron of interest contributes 1 to the value of S. And then for Nd and Nf electrons, each electron within the same group contributes 0.35, and each electron in groups to the left contribute 1. So we're going to get into these two rules more in this example. So let's consider nickel. So the first thing that I want you to do is to write out the electron configuration for nickel. Now write the complete electron configuration. So don't use the normal gas core abbreviation. I want you to write the complete normal gas configuration for this and organize it in the way that I have up here. So that is what I want you to do, and pause the video to do that. And then I'll show you how to calculate this when you're done. So hopefully you paused the video and tried it for yourself. So let's write the electron configuration of nickel in the correct form that Slater wants us to use. So nickel has the configuration of 1s2. So this is our first group. 2s2, 2p6, so this is our second group. 3s2, 3p6, so this is our third group. And then remember the D subshell is its own group in itself, so 3d8, and then 4s2. So we have 1, 2, 3, 4, 5 groups here. So the first thing that I'm going to do is I want to find out the effective nuclear charge for a 3d electron. So how would I go about doing that? So let's go back to our rules here. And the first rule that is relevant to this calculation is Rule 5a. So 5a states that each electron within the same group contributes 0.35 to the value of S. So all I have to do is look at my group here, so in this case my 3d8 group, and multiply the amount of electrons within that group minus 1 times 0.35. So instead of multiplying 8 by 0.35, we only multiply 7 times 0.35. And we do that because we aren't considering our electron of interest within the calculation. Because our electron of interest is within the 3D subshell, so we sort of neglect that from our calculation. So the next rule that is important to this particular calculation is Rule 5b. So 5b states that each electron in the groups to the left contribute 1 to the value of S for an Nd electron. So what we do is basically add up all of the electrons below our 3D8 subshell, or our 3D8 group. So we have 8 from this group, we have 8 from this group, and then 2 from this group. So 8 plus 8 plus 2 is 18. So we add to this 1.00 times 18. And when we add all of this together, you should get something around 20.45. So we find our Z effective for our 3D electron from our particular equation. So Z effective is equal to Z minus S, and Z is equal to 28. And remember, Z is just equal to the atomic number minus 20.45, and you should come out with a value equal to plus 7.55. So that is your Z effective for a 3D electron. So the next thing that we want to calculate is the 4s electron. So the 4s electron is found within this group right here. Right? So it's found within this group. So let's look for one of the rules that would apply to our situation. So our particular situation states that each electron within the same group of interest contributes 0.35 to the value of S. And the only exception is the 1s electron, which contributes 0.30 to the value of S. So in this case, since we have a 4s electron, we can use the value of 0.35 in order to find our particular number that we need. So we take 0.35, so 0.35 times 1, because once again, our electron of interest is within this group, and there's only one other electron within that group. So 0.35 times 1. So what's the next rule we need to use? Well, the next relevant rule is rule number 3. And rule number 3 states that each electron in groups with a principal quantum number of n-1 compared to that of the principal quantum number contributes 0.85 to the value of S. So in order to calculate this, you just have to look at these two groups, right? Because these two groups have a principal quantum number equal to n-1 compared to the electron of interest. So we have 8 electrons from here, and then we have 8 electrons from here and 8 electrons from here. So therefore, we multiply 16 times 0.85. However, we're not done yet. We also have these last bit of electrons here. And the rule that applies to this is rule number 4, which states that electrons in groups with a principal quantum number of n-2 or greater compared to that of the principal quantum number contributes 1 to the value of S. So therefore, all we have left is 10, so therefore 10 times 1.00, and when you add all of these together, you should get a value of 23.95. And now our effective nuclear charge is equal to Z minus S, and Z is equal to 28, which is the atomic number of nickel, minus S, which is 23.95, and the answer that you should get is plus 4.05. So that is the effective nuclear charge acting on the 4s electron. So that is how you use Slater's rules in order to find the value of S. So it's just basically following the rules and adding things together. It's not too bad, right? Okay, so the last thing that I want to talk about in this video before the practice problems is basically the general trends or general behaviors of the nuclear effective charge. So on the periodic table, when you go from the bottom to the top, the effective nuclear charge increases. And when you go from left to right, your effective nuclear charge increases as well. However, when you go from right to left, you have a decreasing effective nuclear charge, and when you go from top to bottom, you have a decreasing effective nuclear charge. So when you go from bottom to top, your effective nuclear charge increases, and when you go from left to right, your effective nuclear charge increases. However, when you go from top to bottom, your effective nuclear charge decreases, and when you go from right to left, your effective nuclear charge decreases as well. And what is the reason for this? Well, as we move from left to right, our effective nuclear charge increases because our atomic number is increasing. And remember, atomic number is equal to the number of protons in the nucleus. So as the atomic number increases, Z increases. And you may remember from Slater's rules that electrons within the same electronic shell don't really shield each other too well. So therefore, Z increases much faster than S increases. So Z increases faster than S increases. Therefore, the effective nuclear charge increases as we move from left to right. Now, the effective nuclear charge decreases from top to bottom because as you go from top to bottom, you are adding new electronic shells as you go down. So as you, let's say, go down from group 2 to group 3, you add a whole new electronic shell to that particular atom. So therefore, your shielding or your screening constant increases much more than your atomic charge, than your nuclear charge. So therefore, Z effective decreases as you go down. And that's because you're adding more and more shells as you go down. However, as you go from left to right, your atomic number increases and your Z effective increases much quicker than your screening. So this is the general trend. So we can write out these rules for you quickly. So as we move left to right, Z increases faster than S increases. Therefore, Z effective increases. And this is basically due to the decreased ability for electrons within the same electronic shell to screen each other. As we move down a group, Z increases much slower than S increases. Therefore, Z effective decreases as we move down a group, and this is because we are adding new shells to the electronic structure. So those are the rules. As you go up the periodic table from bottom to top, your effective nuclear charge increases, and as you go from left to right, your effective nuclear charge increases as well. So that is it for the lecture today. Here are some practice questions for you to try for yourself. I encourage you to pause the video and to come back once you are done. So the first thing that I ask you to do is to calculate the effective nuclear charge for a 3p electron in a sulfur atom. So the first thing that you got to do is write out the correct electronic configuration and the correct groupings. So you start out with 1s2 as its own group, and then you have 2s2, 2p6 as its own group, and then 3s2, 3p4 as its own group. So we're looking for the 3p electron. So in order to find the 3p electron, you have to look first at its own group, so the 3s2 and 3p4. So you have 3 electrons from the p subshell, because we're not considering the electron of interest, and then the 2 from the s subshell. So therefore, we have 2 plus 3, which is 5, so 5 times 0.35. So the first thing that you got to do is find out how much these two particular groups add to the screening constant. So the rule that applies to this one is the n-1 rule. So therefore, we're going to look at this group. So we have 2 electrons from the 2s subshell and 6 from the 2p. So this is equal to 8 times 0.85. And then the last bit is the n-2 rule, which states that 1.00 times 2. So that's because we have 2 from this group. And then when you add all of this together, you should get something around 10.55. And then when you find z effective, you get equals z minus s. So therefore, z is equal to 16 minus 10.55, 5.45. And that would be the effective nuclear charge for a 3p electron. So the last little bit is to rank the following elements from least to greatest for their effective nuclear charge. And remember, for the periodic table, your effective nuclear charge increases as we go up, and it increases as we go from left to right. So therefore, we just got to follow that trend. And when you follow that trend, you'll see that rubidium has the highest n value, so it's in period number 5, so that's the lowest. So the next one would be potassium. Then after that would be lithium. And then after that would be carbon, and then oxygen. So this would be from increasing Z effective. And that is it for effective nuclear charge. So I hope this video helped you with these concepts. And in the next video, we're going to be talking about, I think, ionization energy. So I hope to see you in the next video, and good luck, everyone. See you next time.